Hi, I'm Jess Chellino. I'm a PhD candidate at the University of Florida, and today I'm going to talk about the work I've done on analytic covariance matrices for the endpoint correlation functions. Before I get into this project, I want to point out that this is a good time to work with NPCFs because NPCFs require spectroscopic data, and we have a lot of surveys taking spectroscopic data that are either currently online or will be online soon, and these include DESI, Euclid, Rubin, and SPHEREx. I'll start with some background and motivation for this project, and then I'll get into the model that I use for the power spectrum. I'll then show how I use this model to obtain an analytic covariance matrix for the two-point function, as well as the F integrals that are the building blocks of the higher order covariance matrices. I'll then give a comparison of my model results to true results, explain how I can use my model results to find the precision matrix or the inverse covariance matrix, and conclude. So now for some background and motivation. The endpoint functions tell you about the clustering of galaxies above what you would expect from a random distribution. So for the two-point function, you would have two galaxies separated by some distance r. You need to look at every possible pair of galaxies in your sample and compare that to what you would expect given a random distribution of those galaxies. The three-point function involves three galaxies. You choose one as the primary vertex and measure the distances to the other two galaxies. And you need to do this for all possible triplets in your sample. And the four-point function is similar, where you have four galaxies and you measure the distances between them and find all possible tetrahedra in your sample. The endpoint functions are very useful because we can learn a lot about the BAOs, neutrino mass, the galaxy halo relationship, the cosmic expansion history, as well as magnetohydrodynamics in the ISM, and recently whether parity violation exists in large-scale structure. Now, when we do an analysis with endpoint functions, we need to constrain our measurements with a covariance matrix, and we really need the inverse of the covariance matrix to optimally weight our data. The covariance matrix essentially tells you about how independent one shape in your sample is from another of the same shape. So for the two-point function, for example, you would have a pair of galaxies correlated with another pair of galaxies separated by some distance s. And in the covariance matrix, you need to correlate all possible pairs of galaxy pairs. Now, for the covariance of the three-point function, you would have to correlate all possible triplets of galaxies in your sample with all other possible triplets of galaxies in the sample. And the same thing for the four-point function, where you're correlating all possible tetrahedra with all other possible tetrahedra to get the covariance of the four-point function. Now, throughout this talk, I'm going to use a convention where one shape will have side lanes that are unprimed, and the second shape will have side lanes that are primed. And in each case, we're talking about the separation S being the distance between these shapes. Now, the covariance matrix is normally obtained from mock catalogs, but we really need the inverse of the covariance to constrain our measurements of NPCFs. And this is really prohibitive when you have a high number of degrees of freedom in your analysis because the mocks become too noisy to invert. You essentially need several mocks per degree of freedom so that your covariance can be smoothly invertible. And people have come up with different solutions to work around this. These include data compression, jackknife resampling, and the analytic covariance, which is what I'm going to be focusing on for the remainder of this talk. So the motivation here was that we wanted to find an analytic covariance matrix so that we could understand the structure of the covariance better. Here I'm working in the Gaussian Random Field, or the GRF limit. This assumes that the density field is a GRF, and all of the correlations are the 2PCF or products of the 2PCF. Now I'll get into how I modeled the power spectrum. The power spectrum traces the clustering of matter as a function of scale. Because the covariance depends on integrals of the power spectrum against spherical Bessel functions, we wanted to choose a simple power spectrum model that would allow us to evaluate those integrals, which I'll show later. So we decided to use a power law model for the power spectrum, which is shown here. So we have an amplitude A over the wave number. This is a physical piece. And then we have a shot noise term, which is 1 over the number density of galaxies. So throughout this talk, when I refer to the model power spectrum, I'm talking about this equation here in the purple box. When I refer to the true power spectrum, I'm talking about that computed from CAM, the code for anisotropies in the microwave background. So here I'm showing the dimensionless power spectrum, delta squared. Um, this is because our power spectrum really enters our covariance with the weighting given by the dimensionless power spectrum. So here our model is the dashed red line, and the true power spectrum or the CAM power spectrum is the blue solid line. And you can see that they match up pretty well, except for at low values of K. However, this deviation at low K does not have a significant effect on our covariance matrix, so our power law model for the power spectrum is accurate to use. Now I'll get into how we use that to find the analytic covariance of the two-point function. This first equation here gives the covariance of the two-point function. We have two spherical Bessel functions of order 0 against the power spectrum squared. If we plug in our power spectrum model, we're able to evaluate this integral in terms of two quantities, g, which is the geometric mean of the side lanes r and r prime, separating the pairs of galaxies, and chi, which is the ratio of the side lanes. We also have physically relevant quantities such as n, which is the number of galaxies in our sample, and g, which is the number of galaxies within a sphere with radius set by the geometric mean, r and r prime, and eta, which tells you about the scale of cosmic variance shot noise equality. Now, when we evaluate the covariance matrix of the two-point function using our power spectrum model, we end up with this result. So you can see we have our physically relevant quantities in here. These h's are Heaviside functions, so this term only contributes when 1 is greater than chi, and similarly down here. These thetas are also Heaviside functions, and the product of them tells you that this term only contributes when r and r prime are equal, and then we also have a direct delta term. Now, something that I want to point out are these factors of g over eta. If g over eta is greater than 1, the physical part of the power spectrum dominates over the shot noise piece. If g over eta is less than 1, the shot noise piece dominates over the physical part of the power spectrum. So with the way we evaluated the covariance with our power spectrum model, we were able to get an analytic covariance in terms of physically relevant quantities that tell us about the behavior of the covariance. Now I'll go on to the F integrals, which are needed to find the covariance matrices of higher order endpoint functions. The covariance really depends on products of F integrals, where the F integrals are defined here. They're of the power spectrum against three spherical Bessel functions. These Bessel functions have arguments Ri, which are the unprimed side lengths, R prime J, which are the prime side lengths, and S, which is a separation between the shapes. And the orders of the spherical Bessel functions here are L, L prime, and L double prime, corresponding to those side lengths and separations. We really need two different cases of these F integrals to find the covariance. So the first has one SPF with order 0 and argument 0, and the other has no SPF with order or argument 0. So I'll start with this first case where we have one SPF with order and argument 0. In that case, our F integral reduces to this equation here, where we've plugged in our power spectrum model. We're able to evaluate this in terms of relatively simple functions. So here again we have Heaviside functions, which says that this term only contributes when r is greater than s. This term only contributes when s is greater than r, and both of them are proportional to the Gauss 2f1 hypergeometric functions. Essentially, those are power series of the argument, which is s over r squared or r over s squared. And then finally, we have a direct delta term, which only contributes when r and s are equal. Now, if we move on to the second case of F integrals we need, this is where we have three SPFs without order or argument 0. If we plug in our power spectrum model, we're able to evaluate this analytically. And before I show that result, I want to go through some definitions of the functions that I have in that result. So first, r plus or minus is the magnitude of the sum or difference of the side lengths divided by the separation s. F plus or minus and F1 are hypergeometric 3F2 functions. The important part here is that they're power series of their arguments, so either r plus or minus squared, or 1. And then we also have these major g functions, which are contour integrals in the complex plane. And again, depend on the argument, which is either minus r plus minus squared or minus 1. So now with these definitions, I'm going to put up the result for this purple boxed f integral. So this is our result. The important part here is that we have 4 sums up here, and they're all finite. You can also see that we have our hypergeometric functions in here, as well as our major g functions. Again, we also have Heaviside functions, and this is a really important part of our result because we're able to break our result into different regions. So first, we have a Heaviside of 1 minus r plus. This term only contributes if the separation S is between or is greater than the sum of the side lengths in the unprimed and primed shapes. Our next term in red here is a product of 2 Heaviside functions. This term only contributes in the region where S is between the sum and the difference, the sum and the magnitude of the difference of r and r prime. And then finally, our r minus minus 1, our Heaviside of r minus minus 1, contributes when the separation S is less than the magnitude of the difference between r and r prime. So we really only need to evaluate one of these blue, red, or green terms at a time when we're evaluating the covariance, because we were able to break our result into different regions corresponding to how the separation relates to the side lengths and the shapes. Okay, so now that I've shown the analytic results for the f integrals, I'm going to go through a comparison of our model f integrals to the true f integrals. So we've tried this for many different cases that I'm showing here, but in each of these plots, we evaluate the f integral, which is the power spectrum with 3 spherical Bessel functions in an integral. Here we're plotting these for a separation s equals 50 megaparsecs over h. Our top row is using our model power spectrum to evaluate the f integral, and the bottom row uses the CAM power spectrum. You can see that overall, our model power spectrum accurately reproduces the CAM power spectrum. Our model is less accurate for lower SPF orders, such as the 0, 0, 0 case, where we have more support at higher values of r and r prime. And also, as the SPF orders LL prime, L double prime increase, we see more oscillatory behavior in the f integrals. Now, these black dashed lines trace the Heaviside functions that I showed in the analytic result. Within this rectangular region bounded by these black dashed lines, that is the region where r prime, and s may form a closed triangle. And what we're seeing here is that the f integrals have the greatest contributions to them when it's possible for r prime, and s to form a closed triangle. Now, this was for the separation 50 megaparsecs over h. We've also shown the f integrals for various separations. And now the separation is increasing as you go from left to right across this slide. So we can see that as the separation increases, the rectangular region becomes larger, meaning that we have more possible combinations of r prime, and s that can form closed triangles. However, as we increase the separation, we also have lower support within this triangular region. But again, we see for all separations that the greatest contribution to the f integrals occurs within the region where it's possible for the separation and the side lengths of the shapes to form closed triangles. Now, if we recall, I said earlier that the covariance depends on integrals of products of the f integrals. We can use that to figure out how the f integrals propagate to the covariance. We've seen that the greatest contributions to the f integrals are within the triangular regions. So if you take the product of f integrals as needed for the covariance, that will lead to a sparse covariance. Now, if we look at this example here, we have a product of 2 f integrals. The first one of r1 prime, and s will have the greatest contribution when those 3 sides are able to form a closed triangle, which is in this dashed red triangle. The second f integral will have the greatest contribution when r2, r prime 2, and s are able to form a closed triangle, which is given by the blue dotted region. And if we take the product of those as we would need for the covariance, we can see that outside of the overlapping region, which is given in purple here, the covariance will be near zero. So by identifying that the F integrals have the greatest support when we can form closed triangles, we're able to say that this is what causes sparse covariance matrices. Now, the last thing I want to talk about is precision matrices, or the inverse of the covariance matrices. We really need the inverse covariance, not the covariance, when we do an analysis with NPCFs. But as I said earlier, it's notably difficult to invert covariance matrices. However, the analytic formulae that I showed throughout this work are invertible, and we can use those to find the precision matrices. So first, we can decompose the covariance C into our model covariance with my analytic formulae, C model, plus epsilon, which is some small correction term. Then using a matrix inversion lemma, we're able to invert the covariance so that we only have to invert C model, which is composed of my analytic formulae, which are invertible. Now, we have checked that epsilon is a small correction matrix. I'm showing that here for the covariance of the 3-point function as well as the 4-point function. For the 4-point function, we broke it into the even and the odd modes separately. In these first two plots for the correction matrix to the covariance of the 3-point function and the even 4-point function, I'm zooming in on the greatest contribution to the correction matrix. Outside of what I'm showing in these first two plots, it was very close to zero. And these two plots are really showing you the lowest order spherical Bessel functions. Now, for the correction matrix to the covariance of the odd 4-point function, I haven't zoomed in on a set region because we don't see the same trend there. What we do see is that our greatest correction is along this main diagonal. But what this is telling us for all of these plots is that our correction matrix epsilon is small, and we're able to use the matrix inversion lemma with my analytic formulae and the correction matrix to invert the covariance. Okay, and now I'd like to summarize. So first, I used a power law model to model the power spectrum. With this model, I was able to obtain the analytic covariance of the 2-point function as well as the analytic results for F integrals, which compose the higher order covariance matrices. I found that the F integrals have the greatest support when R prime, and S can form a closed triangle, and this leads to sparse covariance matrices. And I also found that there's a small correction matrix that can account for the difference between my analytic matrices and the true matrices.